All right, guys, here we go. So I'm going to go over this real quick. This is what we did on Friday. If you guys remember right, just remember, don't worry about this simulation approach. It was something we used to do. And since we don't have the new book yet, we're not worrying about it anymore. So when we deal with these, we're dealing with two different heights. So we've got two different distributions. So we know that the difference is going to be male minus female, and so that's the idea. It's 69.5 divided by 65, and then the standard deviation of each one is kind of what we're dealing with there. Okay, so as we work our way through this, they want the probability that they're taller. So if we move this around, it's going to be that the difference is greater than zero. So the probability that the difference is greater than zero. So when we're dealing with probability, remember now we just want to find out some sort of shaded area of the graph, and we want to know that, and we're going to go back to normal, and I know it's in highlighter, normal CDF. CDF. And if you were in class, you got that. So we're dealing with normal CDF right now. Now, what we can make conclusions about the shape, center, and spread, if we're creating a new equation with two different populations, X and Y, we're just going to take the expected value of each one and we're going to add those expected values together. And then if we're going to take the standard deviation, we're going to take the standard deviation of both of them together, and we're just going to take the standard deviation squared times plus the standard deviation of y squared, and we're going to take the square root of that. So if we do that, we can come up with a non-simulation approach, and that approach is just going to be what's the expected value of the male's height minus the expected value of the females, and I get 5 inches. That says inches. Too much coffee. And then so when I need to find the standard deviation, I take both of them, I square them, I add them together, and I get a standard deviation of 21.25. And then that comes out to 4.61 inches. At that point, I can find out the probability that the male is taller than the female. I plug it into normal CDF. My left boundary, because I want greater than, my left boundary tells me that greater than boundary is 9999. You can use 999. You can use 100, as long as it's a really big number. And I know my mu of the difference is 5, and my standard deviation is 4.61. And so the probability that's going to happen is 86.1%. So we just keep working that whole idea. So this one came up, and so they want to find the probability. Where are we at here? They want to find a probability that the sum of the 12 apples is less than the 100. So the probability that the total amount of apples, total, T for total, of all the weights of the apple added up, so there's 12 of them, the weight of each apple, they want to know the probability that it's less than 100. So the total weight is everything that's there, and it's going to be 12 apples. Now, we don't know the value of the apples. All we know is we know that there's an expected value of 9 ounces, just 9 ounces. So we're not sure where that is. And so what we do is we take the expected value of one apple, add it to the expected value of two apples, to the expected value of the third apple, the fourth apple, the fifth apple. We keep going until we add 12 apples up, which gives us 108 ounces. So this became a point of discussion in class. Can't we just multiply the standard deviation by 12? No, you can't. Even though we did that the day before, we did it the day before because we were multiplying the mean by 12. So if we multiplied the mean by 12 to create a larger mean, we would create a bigger standard deviation. We're not doing that. We're adding each expected value together to get a total weight. It's a total weight that we're looking for. So therefore, we have to find the total distribution, which means we have to do 1.5 squared plus 1.5 squared plus 1.5 squared. So we have to deal with the formula of the 1.5 squared. That gives us the square root of 27. Since we want less than, we've got our boundary on the left side. put our 1 or 100 or 108 as the up mu, and then our standard deviation is 27, and that gives us a value of 6.2% or 0.0621. So we talked about this a little bit. Are they independent? Absolutely. One student's choice does not affect the other. Okay, so we look at this here, and so that just means we're going to add the two values together, just like we said before. This is from the calculations, I think 2 days ago. The expected value was 14.65 units. They give us 15 in this one, which is right here. They give us 15 right here. We add those up, and it's 29.65 units. If we're looking for the variance, it's the unsquare rooted version. So the variance is 9.5. Again, this comes from the same data as that one does. This one comes from the problem where they give us. And then we get our standard deviation of 3.08. And you can interpret those from there. But we just wanted to calculate the two. So on this one, we're looking at this here, another example. Again, they give us a little bit of information here. We know that the community colleges have $832.5, and we have an overall cost, and the overall cost is from that piece plus the cost of books, and the cost of books is 153. So if we add those two together, the expected value of units and book cost is 832.5 plus 153. Now, we cannot calculate the standard deviation because books and units are not independent of each other. So in other words, if I take more units, I'm going to pay more than likely, because I have to buy more books. So since they're not independent of each other, it violates the rule that we can't find standard deviation. So that's our little bit of help. And tomorrow, Monday, we're going to start tackling binomial distributions, which is some serious voodoo math. So here we go, guys. Talk to you later.